Hi, hello everyone. This is XiaomingLiu from Michigan State University. I'd like to thank the organizer provide this opportunity to allow me to share some of our work in autonomous driving. So today I would like to focus on monocular vision-based 3D perception work. As you're all understanding, for autonomous driving, 3D perception is very important because giving any sensory input, we like to be able to understand object and their motion in the 3D space, right? In terms of 3D detection and tracking and as well as forecasting. So in order to achieve 3D perception, we need a different variety of sensors such as LiDAR, RGB, as well as radar. And sometimes we might need a multiple of each of those sensors. However, in computer vision, we always like to solve a immerse problem. That is, what if we don't have a depth sensor, we only have RGB images? From RGB images, how much we can do 3D perception. So this has been the focus of the lab in the recent years. So in particular, I like to focus on two different problems. That is giving RGB, sensor input. How can we do 3D object detection and 3D object reconstruction? So in particular, 3D detection means that I will be able to detect object in a 3D space, and the bounding box will be a cuboid instead of a 2D bounding box. So I will know the spatial location of those boxes in the 3D space. This is the definition of 3D detection. And in addition, we also like to do 3D reconstruction. That is, giving a bounding box of the object, I like to reconstruct its 3D surfaces. So once this reconstruction is done, you could actually look at the objects from different view angle. And so this is a interesting two problem, kind of quite relevant because detection is a front end, the reconstruction is trying to get further detailed three-dimensional structure information. So let's start with the first one. So this work was published in ICCV in 2019 with my student Garrick. So as we said, the monocular 3D detection is the basic idea is that giving an input image or video sequences, how can we detect the object, including cars, pedestrians, and cyclists in the 3D space with 3D bounding boxes. And we formulated this problem as a three-dimensional region proposal network approach. So there has been previous work, on this topic. But if you look at previous work, they either use external network or they require multiple stage of approach to solve the problem. For example, this was work published in CVPR 2017, and this was work in CVPR 2018. So in both network, you can see that the 2D RPN in one as well as depth estimation in two, these are the external network, and they are frozen in this training as well as testing process. So eventually the network architecture will become fairly sort of bunky because of those additional networks. In comparison, our approach is more integrated approach that we have a single model, be able to take video as or image or video as input to be able to produce 3D detections. So we don't require any external network to do it. And eventually our network will also be much more efficient compared to previous work. So in our approach, one of the innovations is that how do we define anchors, right? Because previous method mostly treats 3D detection as a 2D detection problem first. Once you detect in 2D boxes, then you fit 3D bound box around the 2D results. However, we form this problem as begin to start with a 2D detection, a 3D detection problem. That's why we have anchors in 3D space. So the anchor are quite important basic kind of unit in any of the detection work. In particular, we define anchor in terms of two dimensions, for example, horizontal height as well, horizontal width as well as height. This is a 2D space. In 3D space, we define HLW, that's width and length and height. As well as we define theta 3D, that's 3D rotation angles. We also define how is the 3D point to be projected into 2D. This is XYZ in the projected space called XYZP. So with this equation, we are connecting the 3D points information, which is XYZ 3D, with a 2D projected location, that's XYZ P, through the projection matrix. And also for the theta 3D, it's defined as observation angles, which, as you can see, we will be find the axis of the car first, then the angle will be with respect to the axis. In addition, in order to generate anchors, we take a clustering approach, that is, based on the H and W in 2D, which mostly are the different size of the cars, we do clustering and separate them into different clusters. Then for each cluster, we'll be computing what's the statistic of the ZP and the WHL theta. Those are the 3D coordinates, 3D size information. So you can see that in general, we find that the small car typically corresponding to larger ZP, which makes sense because that means that the car will be observed will be parked at a further distance, at a longer distance compared to the camera. While bigger cars typically have smaller ZP, which means that they are more closer to the camera. And in addition to the ZP, they also have other statistics, for WHL theta. And this step are kind of important because only with this step, we are able to figure out what are the different statistics of the car distribution in the 3D space. So this will be very helpful for us to later to do the regression based on the anchor. Okay, given this, now we can compute the default anchors, right? So these are the default 12 different anchors we computed according to the statistics. You can see that they have their a priori distribution in terms of their size and location as well as orientation. Once the anchor has been defined, and now as you can see, we can place the anchor, right, in different location on the imagery. And this location will essentially fed to the network to ask CNN, is any of those locations closer to the ground truth? If they have sufficient overlap with the ground truth locations, then we will be regressed from the anchor location into the final ground truth bounding boxes. So this is what CNN try to learn. But the anchor provide a good candidate in terms of what are the potential locations of the cars in the 3D space. So with this, and in the supervision, as we said, right, we determine whether each bounding box will have sufficient overlap with the ground truth. If the ROU is more than 0.5, then they will be essentially ask the network to learn a transformation. So the transformation will learn a set of parameters including C and X, T, Y, T, and the ZTP, as well as 3D deviation as well as 2D deviation. So each one of the parameters essentially tell the network how much deviation I want to apply to the anchor, so that eventually the estimation results will be matching with the ground truth. Okay, so this is starting from anchor. We learn this deviation parameter and moving to the target. Now, this set of equation to this is essentially trying to tell us that giving the anchor parameter and giving the transformation parameter, how can we eventually convert into the final target location? So here, all the primes, x prime, y prime, z prime, as well as whl prime, they are the updated location. While the variable with color, they are the network output. And the rest of parameters are basically anchor parameters such as W2D and H2D and ZP and so on and so forth. And similarly, the right-hand side try to convert the 2D location from the anchor to the target boxes. So with this conversion, as you can see, we're also using a loss function, right? These are three different loss functions. One is classification. Second is the 3D bounding box consistency, as well as 2D bounding box. So the three loss function will be used together to do the training. So in terms of architecture, we start with a very base network, which is a dense net. And then we have two different streams. One is global stream and try to estimate the parameter. Second is a local stream. So this is one of the novelty we have in the algorithm. That is, we think that for different size of the car, when they are at different distance to the cameras, they should have different filters for the convolution. For example, in the close-up range, you may have a filter for the tie of the car because the tie is very visible feature to detect the cars. However, for cars at further away distance, maybe that tie is not that visible. You don't have this kind of convolution filter for that. So this scheme allows us to do depth-aware convolution, so-called. And eventually, the two scheme will be combined together and produce a final estimated parameter. So this is the variables in the red box. These are essentially the estimated final parameters. Okay, let's look at some results. So in general, people do experiments in two cases. One is bird eye view, and second is 3D detection view angle. So the criteria is very strict. The IOU need to be larger than 0.7, and we test on two different sets, validation 1, validation 2, as well as test sets. Okay, so you can see that we compare with the recent work in this space. There are four recent works. And we have three different sets, easy, moderate, and hard. Of course, easy has highest performance and harder has the lowest performance. If you compare with previous work, you can see that improvement margin from previous work is quite high. For example, in the moderate for bird eye view, we improve from 12% into 19%. And for the 3D detection, we improve from 5% into 16%. Okay. In addition, our approach is also more efficient compared to the previous work, such as reference number 4, because they did use multiple networks. And looking at quality results, so you can see this is the detection result for cars, and this is including cars and the pedestrian. By the way, we have a single model that can work with three different object categories. So this will be showing a cyclist, pedestrians. So let's look at this video. So this video is interesting to see, and you can see that in the bottom we have the bird eye view, and on the top, we have the original video with overlay bounding boxes. In the bottom view, every single cell is 1 meter, both horizontal and vertical. You can see that we're doing the detection in the range from 0 meter all the way to 60 meters. So every detected object will be shown at the box as a rectangle in the bird eye view. So as the driving is going through, we are seeing more and more detected objects. So one interesting thing is that you can see that right now one issue is the detection is not very stable in the video sequences because this is still an image-based detection solution, right? Sometimes the box is kind of flashing, especially the orientation is very unstable. So this actually leads to our more recent work where we are taking a video-based approach where the detection result is much more stable in our more recent work. Hopefully we can share with you in the future. Okay, now move to the second part. I'd like to talk about monocular 3D object reconstruction. So this is our recent work still under review. And the basic idea is that giving a single image of any generic object such as car, chair, and airplane, we like to be able to reconstruct its 3D surfaces. And so by using a single model, so once reconstruction is done, you can look at the surface from any view angles. Of course, this problem has been studied previously, but there's a few limitations. First of all, the quality of the 3D shape might be limited. Either people only do 2.5D reconstruction, or the 3D surface quality is not high. Secondly, many of the previous work only apply or test on the synthetic data, not on the real kind of wild data, which is our focus. And so one of the reasons that the people cannot, train test on the wild images is because for wild images, you don't necessarily have to ground truth. You don't have the ground truth 3D information. So therefore, you cannot really use them for training, right? One of the innovation in this work is that we are kind of modeling the appearance and the geometrical simultaneously so that we can do inverse graphics kind of approach so that even the real data can be utilized in training. That's a key contribution. So as we said, we like to be able to train test on the real images without 3D ground truth. And we want to have a complete generic object modeling in the sense that giving an image, we like to have segmented 3D shape and pose information and albedo information and lighting information. Eventually, all of them combined together should be able to synthesize the original input image. So this is basically analyzed by synthesize, in the sense that if all 4 elements could be estimated correctly, then the combination of them, the rendering of those 4, can reconstruct the original image. So of course, design need to be careful in terms of having very efficient image formulation process, so that you can train this end-to-end in the system. So this is the overall idea. Giving an input image, we have an encoder to learn 4 different elements: lighting, L, camera projection matrix P, FS is a shape latent code, FA is a albedo latent code. Eventually, the FS and FA can be sent into 2 different occupancy network, DS and DA, which is essentially 2 different decoder, one for shape S, one for albedo A. And afterwards, the 4 elements, that's LP and the shape, the albedo, can be combined through the rendering layer and render the original image. So hopefully this reconstruction image is similar enough to the input image. So this is essentially a self-supervised loss. So if you think about it, this is essentially including model learning, that's essentially the DS-DA learning, as well as model fitting. Model fitting is E is encoder. So we are basically doing the model learning and model fitting simultaneously within the same network. So some details, in terms of shape representation, we have the DS. DS essentially serve as occupancy network, where FS is a shape code, the XYZ are the 3D location, and the system will try to learn a mapping function to learn its occupancy. So here you can see that whenever the point is inside the shape, the learned result should be 1, otherwise it should be 0. So one interesting thing is that we have 4 different branches try to learn the unsupervised segmentation of the shape, so that every time, if hopefully for the similar XYZ, it will be occupying the same one of the 4 branch. We have O1 to O4. These are the branch index. Yeah. Similarly, we do the same thing for the albedo encoder. So you can see the albedo, we're also learning the different albedo, which is C1 to C4, for hopefully for different parts. And eventually, one albedo will be chosen by which shape parts you will be selected. So K indicate which one of the 4 shape parts you are corresponding to, and then the K will be used to select one of the 4 RGB-based albedo information, and this will be the CK. So in the bottom, we're showing you that for a typical car, what are the 4 different parts look like, and their corresponding albedo information for the different parts. So this is the overall scheme to show you how the rendering is done. Basically, giving a ray from the camera, right? We are trying to find the intersection point on the body of the car, and this XOV point will be sent into the DA, that's albedo decoder, generate albedo information. And the albedo information will be multiplied with the lighting as well as surface normal, eventually produce the RGB color for that pixel. That pixel will be sent into the rendered image. Similarly, you can do other points through the ray tracing. And okay, in terms of training, we have 2 different stages. First stage, we only train with synthetic data. So we learn the shape decoder first, and then we learn the albedo decoder and the encoder. And second stage is unsupervised joint modeling, which involve both synthetic data as well as real data. So we have 3 different major loss. Our image is image reconstruction loss. Secondary is silhouette loss. Silhouette loss basically saying that the projection of the 3D shape in the 2D image should have the similar silhouette compared to the estimated silhouette on 2D images. So for real image, we need the silhouette estimation, giving a 2D image of a car. Okay, so this shows you some of the expressiveness of the shape model. You can see that as we are traveling in the latent shape space, we are reconstructing different 3D shapes, right? So eventually you can see that the object reconstruction problem become the mapping, giving image into a correct point in the latent space. And we show you here some of the single view 3D reconstruction work in comparison with previous work. These are the synthetic data reconstruction. So you can see that our approach not only having high quality reconstruction, but we also provide the unsupervised parse information for those input images. Similarly, this on the real data. So you can see that for real data, the improvement on the shape is much more obvious. It's even more obvious compared to the previous case. Okay. Of course, quantitative experiments are being done on different database. So here we have comparison with 4 to 5 previous method in the quantitative experiments. I believe one is on Pascal 3D, one is on Pixel 3D database. So they are two separate databases. Okay, in general for this direction, our overall idea is that we like to be able to do 3D morpho model for generic object. So for example, ImageNet has a 1,000 object category. Can we actually learn 1,000 different 3D models? If we can do, then giving any 2D image in the future for those categories, we can reconstruct its 3D models. So this will be useful for very generic object reconstruction purpose. Okay, so far we've been telling you the middle level vision in terms of detection and reconstruction, but in the lab we're also working on other problems such as low level vision as well as some high level vision tasks. So in the next maybe 2 minutes, I'll just give you some highlight of some of other works. For example, this work we published in CVPR 2019 for depth compression, that is giving a single image as well as the sparse LiDAR signal. Can we actually reconstruct a very detailed depth information? This is called depth compression. So previous has problem that they generate so-called smearing pixels. Basically, those pixels are in between of the foreground and background. They actually doesn't exist in the original data, but they are kind of generated during the depth compression process. While in comparison, our approach generates very sharp background with much less smearing. So here shows you example of where the top left is input, the bottom left is estimated completed depths, and on the right hand side we show you the bird eye view. So you can see that on the bird eye view, the right hand side is our result. You can generate much cleaner, much dense information, and which will be suitable for object detection. So this is our more recent work. We'll be publishing this year CVPR, where the idea is that oftentimes given an image, people trying to do monocular depth estimation. But one thing we find is that if you compare monocular depth estimation with semantic segmentation result, the semantic segmentation seems to provide a much precise boundary information for moving objects compared to the depth estimation. Depth estimation on the boundary typically is very bad, but semantic has a much sharper boundary information. So the idea is that can we utilize the higher quality boundary information in the semantic estimation to provide additional supervision for the depth estimation so that the depth will become better, especially on the boundary area. That's the overall idea. On the high level, our result does improve the previous state of art in terms of monocular depth estimation. And also for the first time, our self-supervised monocular depth estimation has the same performance compared to supervised depth estimation method on the absolute relative depth, which is one of the most important criteria for the measurement for the depth estimation. So this is quite encouraging. Okay, in summary, 3D detection from 2D imagery is just in the beginning. There's a lot of interesting research could be done, and the category-specific 3D reconstruction could leverage a very strong prime. And we think that in the future there will be more interesting computer vision problems in the autonomous driving space. I'd like to thank my student and various sponsors to support our work. I'm happy to take any questions. Thanks.